All right, greetings everyone. There was the question, or somebody asked me to make a video regarding slope fields and some sort of how do you explain whether or not this particular differential equation goes with this particular slope field. And this is, something that just comes generally with practice, but I'm going to show you one quick example, and I'm going to try to do my best to explain the properties of the graph, the slope field, that are associated with the particular differential equation. And from there, hopefully you'll see that connection, and then you're going to try to do that sort of thing in the future anytime you encounter that issue. So here's a picture, and here's a differential equation. And I apologize for the shadow that's down over here in the lower left corner, but I'm running a little behind, and so I got to try to get this picture taken quickly, and it isn't as clean as it can be. So what is it about this picture here that shows you what we're dealing with is the differential equation that's shown up here on the screen? Well, there's a couple things here. The things that you want to start to look for that would identify whether or not this is correct are, one, places where the slope field has horizontal or, let's start there, horizontal line segments. So if you look at the picture, I see that right here, the slope field has horizontal segments when y equals -1. Now, if I look up here at the actual differential equation, that should make some sense, because when I plug -1 in here for y, the whole numerator becomes 0. And since that numerator becomes 0, the whole fraction becomes 0, except when x equals 0, except on the y-axis. But nonetheless, that means y prime is going to be 0. And so that right there is an indication that this is at least a potential correct differential equation for this. And I say potential because maybe there's certainly other differential equations that would have this same property happening, where the slopes are all 0 when y equals -1. Just have any other one that has a factor of y plus 1 in it, and that would be the case. So this here is the first indication that this might be correct. Another thing to look for is what the value of x here. Notice we have x in the denominator. So think about the process of letting x get smaller and smaller and smaller, and what that does, regardless of really what's happening to y, for the most part, to the slope. So again, as x gets smaller, then this whole quotient gets larger in general. Okay, there's an exception to the rule on that, but in general that's true. So if this whole quotient gets larger as x gets smaller, then we should see the slopes get steeper as x gets smaller, either with a positive slope or a negative slope. So if I just pick a line right over here and start to see what happens as I move for smaller and smaller x, so that means in this direction here, smaller in magnitude, okay? Let me be clear on that, smaller in magnitude. Then notice that the lines are getting steeper as I move in that direction, okay? They start with a slant here, it's a little less slanted, and it's a little, this one over here points upward more than this one does over here. And even you can see one right here that almost looks like it's forming a plus with the -3 right there, with a negative in front of the 3. It's not. It's even more vertical than the one to the left of it. And so that indicates that this pattern that I expected numerically is happening. Similarly, if I look from the other direction, as x gets smaller in magnitude this way, again, the slopes are a certain steepness, and then they're getting steeper as we move closer and closer to the y-axis, as the magnitude of x gets smaller. So that is another confirmation that the picture that we're looking at does associate well with the differential equation. What else? Well, we can argue in reverse, too. If we move away from the y-axis, as the magnitude of x gets bigger, we would expect the whole quotient to get smaller. And so we can see that here we have steep, a little less steep, less, less, less. And so that property is holding also. couple other things that we could think about in order to help explain why these associations are correct is to start thinking about the direction of the slope. Is it positive slope or negative slope? Is it sloping up? Is it up or down? And so, what do we see for this? Let me see if I could find what's going on here. So, notice, as we already talked about, when y equals -1, that causes this whole quantity in the numerator right here, y plus 1, to be 0. So I can look, when y is greater than 1 and when y is less than 1 and try to determine some signs. When y is greater than 1, y plus 1 is going to be positive. And multiply by 2 keeps it positive. So for everything above this line right here going this way, y is always positive. Now if I'm to the right of the y-axis, x is positive. And so a positive divided by a positive has to give me a positive number. And so all these over here have positive slopes, which associates with, like I said, positive divided by positive is positive. Now, if I'm below this line y equals -1, then 1 plus y is going to be a negative quantity. So the numerator of my slope of my y prime here is going to be negative. And if I'm still on this side, the right side of the y-axis, or positive values of x, I have a negative divided by a positive, which means all my slopes should be negative. And so all my slopes over here, are negative. And so again, this associates this region here, further confirms that the patterns I see in the graph are associated well with the differential equation. We can continue this. If I move over to the left side of the y-axis and still look below y equals -1, then below y equals -1, my numerator is going to be negative. To the left of the y-axis, my denominator is going to be negative, and a negative divided by negative is positive, and all the slopes here are sloping upward. Okay? And then the last quadrant analysis we could do is if we're above y equals -1, and we're to the left of the y-axis, then above y equals -1 means my numerator is going to be positive, but to the left of the y-axis means my denominator is going to be negative, and so a positive divided by negative gives me all these negative slopes over here. And so, again, the region associates well. So what I'm trying to do in figuring out if a particular differential equation goes well with a particular slope field, I'm looking at the numerical relationships. I'm looking for what causes things to be 0, or maybe to have division by 0. I'm looking to see where, I can determine if the ratio or the whole quantity is positive or negative, so I can see the region having slopes that are positive or negative. Those sorts of associations are what's really going to help me determine whether or not I have the correct graph, the correct slope field for that differential equation. Okay? So go back to its basic number properties from things that you learned long ago: positive divided by positive, negative divided by negative, positive divided by negative, or vice versa. All those sorts of relationships, they do matter, and they come into play in how we look at the graph. Don't overcomplicate it. It's complicated enough as is. Break it down to simple numerical relationships and see if things are consistent. See if what produces zeros in the function produces zeros in the graph. See what produces, steeper slopes produces in the function derivative. See if that produces steeper slopes in the graph, or vice versa, less steep to less steep. Positives to positives, negatives to negatives, and all those sorts of associations. And if you can make those numerical connections both analytically and graphically, then you probably are going to have it right. Now, the only thing is, not the only thing, but one other thing to consider is if you had a differential equation, another differential equation that was given as a possibility here, they may have some of the same properties. If they have some of the same properties, then those properties then you have to look at for the differences between the two differential equations. So if both of them give me, horizontal tangent lines or horizontal slopes, 0 slopes when y equals -1, then I can't use that to distinguish between them. I got to use something else. So then I'm going to look for the other properties that they have that are different. If I keep looking at properties that are the same for both, then I can't tell them apart. I have to find distinguishing characteristics. And if I don't find distinguishing characteristics, then I won't be able to tell which one is which. I hope that was helpful. Go study.